At the end of this online module, you should be able to create a script that adheres to programming standards, execute a script from the MATLAB command window, and suppress output from a command once debugging is complete. Let's look at a problem that will help us begin to understand our learning objectives for scripts. The interior of an office building is warmed by waste heat from lighting and computers. An air conditioner must be able to remove all this thermal energy to keep the interior temperature from rising. An engineer must figure out the rate at which an air conditioner must remove heat to keep the indoor temperature from rising when a building has 20 lights that each emit 100 joules per second and 4 computers that each emit 200 joules per second. The solution to this problem is going to take a few computational steps. It would be better to save them in a file than keep retyping them at the command prompt. So how do we do this in MATLAB? Before answering this question, let's identify the separate computational steps needed. We need to calculate the rate at which an air conditioner must remove heat to keep the interior temperature of the building steady. There are 2 sources of heat in the building that we are concerned with, the lights and the computers. For simplicity, we will assume that these are the only 2 sources of heat in the building that must be removed. Because it is a rate, we will look at the amount of heat per second needed to be removed. First, consider the heat generated by the lights per second. We know that there are 20 lights and each light puts off 100 joules per second of heat. The calculation shows that multiplying the number of lights by the heat generated per second provides the total amount of heat generated by the lights per second. Looking at the units helps us determine the overall units. This is called dimensional analysis. Here, lights multiplied by joules per second per light means that the new unit is joules per second. That is, the number of lights unit in the numerator of the first term cancels with the number of lights unit in the denominator of the second term, leaving only the joules per second. Next, let's consider the heat generated by the computers per second in the building. Similarly to the first calculation, we take the number of computers in the building and multiply it by the heat generated by each computer, giving us 4 computers multiplied by 200 joules per second per computer, for a total heat generated by the computers being 800 joules per second. Finally, let's consider the overall rate at which the air conditioner must remove heat by summing the rates of each of the sources of heat. This gives us 2000 joules per second from the lights added to 800 joules per second from the computers, for a total of 2800 joules per second. Always draft out the steps beforehand and do some calculations so that you know your program works. This is an important engineering habit of mind. We are going to use scripts in order to think about how to manage this in MATLAB. A MATLAB script is a type of MATLAB file that enables programming statements to be saved and executed without having to retype them at the command window. So how do I start? In this course, we will always start with the script template as seen here. In the demonstration that is next, we will walk through the different aspects of the script template for our problem. The template should be saved in a logical place on your computer or career account. Once saved, the template can be opened by locating your file in your folder structure. The file should appear in the current folder. Right-click on the template and select Open, or double-click the file. The script template may come up as docked in your editor window. If you would like to be able to see more of it on your screen, you can undock the editor window by clicking on the small down arrow in a circle that is located in the upper right corner of the script window. This provides a pull-down menu that allows you to undock the template. You can redock the window in the same manner. Always resave the template with a new and descriptive name. I will save my template to the name air_conditioner.m by choosing the Save As option in the pull-down menu. Notice that the file is saved in my current folder. Immediately start to document your script. Documentation is important. It is a very critical part of the work of an engineer. In the context of writing a program, it helps you keep track of your work while solving a problem. It helps you remember what you did later on, and it helps others know what you did if they are trying to use or review your work. The header of a script must contain a description of what the script does and the assignment information, the assignment number, the author of the code, the author's team number, the programmer the author was paired with, if this applies, and anyone else who made contributions to the development of the solutions, if this applies. Notice that each line in the header starts with a %sign. This tells MATLAB that you are writing a comment rather than an executable line of code. The first chunk of code in a script is typically the initialization of variables needed to solve the problem. This is the place where all known values are set to variables. This is also the place where constants, like the gravitational constant, are set. For our problem, we need the light information, which includes the number of lights and the heat each light produces, and we need the computer information, which includes the number of computers and the heat each computer produces. As you assign variables, document the meaning of these variables and their units. There are two types of commenting that should appear. Block commenting describes a set of commands. Here are two groups of information, one for light information and one for computer information. Variable commenting explains the assignment of each variable with its units. You see this next to each variable in the script. Known values should never just appear in calculations because they are difficult to locate if they need to be changed. It is also difficult to determine what these values represent when anyone looks at the M file later on. When values are embedded in calculations, it is called hard coding because you are fixing values within the code. To keep code flexible, readable, and editable, a good programming practice is to initialize variables first, then use the variables in calculations, thus avoiding hard coding. It is very important to save and run often. This allows for us to do debugging, that is, looking for errors and fixing them. Running the script often as you work helps isolate where issues in the code exist. To execute the script, type the name of the M file without the .m at the command window prompt. Note that all the variables that were created appear in the workspace, just as if you typed the variable assignments individually at the command prompt. I want to check my inputs. I see that I entered 2000 for computer heat rather than 200. Let's change that in the script. Once I have made the change, I want to save and then check again. So first, I want to clear the variables from the workspace before I rerun the code by using the clear function in MATLAB. Also, I want to clear the screen by using the CLC function so it is easy to see which output I am considering. Then I rerun the code by entering the name of the file without the .m into the command window prompt. Good! This code is giving me what I expected. Once I am satisfied the variables are set properly, I really don't need to see them anymore, so I can suppress them from being printed to the screen. I do this by adding a semicolon to each line of code. Make sure to place it before the comment. To see what happens, I save the script, clear the variables from the workspace, and rerun. Note that the variables assignments do not appear in the command window, but they do appear in the workspace. Now I can use my variables to perform the calculations necessary to determine the amount of heat generated by the lights and computers that need to be removed by the air conditioner. I will place these calculations in the calculations section of the script. Note how I use my computations made when trying to understand the problem as the basis for my code in this script. Now I can add my computations that use the variables I initialized. In the calculations section, I will begin by considering the heat generated by the office components, which I have indicated using a block comment. Then I add each computation in the appropriate variable comment. Notice that I am using the calculations I have already figured out by hand. Then I create a block for the total heat removed by the air conditioner. Here I also use appropriate block comments and variable comments. Finally, I need to run my code to check my results against my pre-calculated values. I see that these are correct. We would typically suppress these lines of code once we see that they are correct and then formally print the results to the command window. But we will save the printing of results to another online module. Let's go over a summary of this module. We can now save scripts with a descriptive file name. We know how to complete all header information in the script template. We always initialize all variables in the initialization section of the template to avoid hard coding. We comment code in two ways. First, we use block comments to provide explanatory comments on sections of code. Second, we use variable comments to provide descriptions and units of variables. We know how to call a script from the command window to execute, or run, the script. Finally, once all debugging of our script is complete, we suppress outputs of variables to the command window using semicolons.